What's going on, Linear Algebra Bros? It's Mr. C here, and in this video I'd like to introduce the topic of span as well as revisit the concept of a linear combination. Well, the easiest way to think about a span is to maybe connect it to something that we're already familiar with, some prior knowledge that is, and that would be none other than the color wheel. And here I have three color wheels, and it's kind of like an evolutionary sequence of steps here going from left to right. Now I want to look at the color wheel furthest to the right, and all of these different shades of green, yellow, orange, and what have you, these are all some sort of mixture of the starting colors, that is the primary colors, red, yellow, and blue. And as you traverse this diagram from left to right, we start out with our primary colors. We blend them together to get secondary colors. For instance, blue and yellow would give us the secondary color of green. Blue and red would give us purple, and so on and so forth. And we can continue mixing further primary colors and secondary colors to get what are called the tertiary colors. But the idea that I'm trying to convey here is that all of these different colors that we're seeing with the color wheel furthest to the right are some sort of special mixture of the three colors red, yellow, and blue. So in other words, these primary colors form sort of like a basis for these tertiary colors and secondary as well. Now we will be talking about a concept called a basis, but we have to lay some foundational work down. And one piece of that is the span of a set of vectors. And you can think of the tertiary and secondary color wheels here as some sort of span of the primary colors. That is, as we form different mixtures and using different amounts of these primary colors, we create more and more colors, to get a finer tuned color wheel. When we form certain mixtures of colors, we are basically creating a linear combination of what can be thought of as vectors. You can kind of consider the colors red, yellow, and blue as vectors, and as we form linear combinations of those vectors, we get other vectors that make up the spectrum of colors. So there's a strong connection between a span and linear combinations. So it's going to be a good idea to revisit the idea of a linear combination, and we'll do that right now. Let's assume that W is a vector in a vector space V. Then W is said to be a linear combination of vectors V1 through VR, and these come from the set V. If that vector W can be expressed in the form K1 V1 plus K2 V2 plus dot 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 KR VR. And so what this is saying is that W is a mixture of the vectors V1 through VR. Now keep in mind that these K's that we're seeing in front of each vector notation are scalars. So there's a certain amount of the vector V1 added to a certain amount of the vector V2 and so on and so forth, that eventually, once all these vectors are combined, will give us the components of the vector W. Okay, so again, note that each K sub is a scalar, and we would call these scalars coefficients of this linear combination. So a common question that tags along with this sort of idea is whether or not a vector is a linear combination of a given set of vectors. Now we can answer this question if we can find scalars that would be multiplied to these vectors to give us the vector w. So the strategy is to see if you can figure out scalars that would go in front of the vectors v1, v2, and v3. And if we do get specific values of the scalars, then yes, the vector w would be a linear combination of the vectors v1, v2, and v3. I want to do a quick recall before we get to the official solution. Back when we were working with linear combinations and trying to find these scalars, which are also called coefficients, I told you that you could populate an augmented matrix with the components of all the vectors involved. In the first column, we populate with the components of v1. The second column, the components of v2. And then the third column, the components of v3. And this will get augmented with the components of the vector w. And then we RREF this matrix. And hopefully what we get is the identity on the left-hand side, that is the 3x3 identity. And if we do, then we'll have specific values of the scalars k1, k2, and k3 in this situation. So what you would see on the right of the augment bar are the values of k1, k2, and k3. If we get anything funky going on with our REF matrix, such as a row of zeros giving us a non-zero value of any of these k's, then we would not be able to ascertain that the vector w is a linear combination. And there might be some cases where our RREF version of the matrix leads to parametric equations, in which case there are infinitely many scalars for which we could write w as a linear combination of v1 through v3. So without further ado, let's see what situation we land in. So let's form the augmented matrix, and in the first column we'll go to the components of v1, 2, 1, and 4, then 1, -1, and 3, then 3, 2, and 5. And we'll write our augment bar, and then the components of w, which are 6, 11, and 6. Now, when you RREF this matrix, you actually do get the 3x3 identity on the left-hand side. And to the right of the augment bar, we get 4, -5, and 1. Meaning that, yes, w can be written as a linear combination, and moreover, these would be the coefficients required in order to do so. k1 would equal 4, k2 would equal -5, and k3 would equal 1. So I'm going to say yes to answer this question, and I'm going to make a little note. W, in order to get its components using the vectors v1 through v3, we would need 4 copies of the vector v1, added to -5 copies of the vector v2, which I'll write as -5 v2, plus 1 copy of the vector v3, which I'll write as plus v3. Alright, and this is definitely something that's pretty cool to check. Just rewrite all the vectors with their corresponding component forms, combine everything on the right, and you will end up with the components of w. It's kind of a cool thing to see, and if you get some time, definitely something I encourage you to do. But for now, this is the end of the video. I want to thank you guys for watching. Please let me know if you have any questions. Otherwise, I'll see you in the next one.